The morning inside the maintenance with the small sound of electronic systems.
Whether the future sky can continue to withstand the increasingly dense air traffic of today.
The biggest problem of future aviation may no longer be speed, but complexity itself. The young workers continue tightening each bolt and checking each sensor, but above them is a giant traffic system becoming harder to control with every passing year.
For many decades, aviation once believed that stronger radar and faster aircraft would automatically make air traffic more efficient over time.
But the reality today shows that the more technology is added, the more pilots and air traffic controllers must process information in a shorter amount of time.
The modern sky is like a crowded city, with thousands of small decisions being made every minute.
Just one small distorted signal in the coordination system can create a chain reaction for dozens of other flights. Tons. It is in that context that the central question of aviation's future begins to appear clearly. Why does the world want to build simpler? In the normal operating state of today's aviation, every flight depends greatly on ground instructions to maintain separation and avoid conflicts in the air. Air traffic controllers must constantly observe radar and transmit voice commands to each pilot to adjust altitude, speed, and direction almost minute by minute.
This model once worked very effectively when the number of aircraft was still low and air traffic density had not yet reached today's global scale.
The female engineer opens a simulation board and shows that just the area around a major airport can contain hundreds of simultaneous navigation commands at the same moment.
Each matte gray metallic narrow-body aircraft must continuously update its position with the central system to prevent dangerous crossings between flight paths. For many years, the aviation industry built a philosophy that humans on the ground must be the center of control, while aircraft mainly execute commands.
That places most of the pressure of processing air traffic on the people sitting before radar screens on the ground, instead of on the aircraft themselves in the sky.
The system is increasingly like a giant network, requiring thousands of people to coordinate just to keep everything from colliding. This heavy dependence on centralized coordination is exactly why aviation has begun thinking about changing its operating philosophy for the future.
Questions begin to appear when global air traffic grows faster than the expansion capacity of traditional air traffic control systems.
Large airports continuously face airborne congestion, causing many aircraft to circle for dozens of minutes just to wait for landing.
The female engineer shows a report in which just one small weather change is enough to disrupt hundreds of flights across multiple countries in sequence.
The young workers inside the maintenance hangar begin to notice that modern aircraft systems are becoming increasingly intelligent, yet their full capabilities are not being used.
Aircraft today can analyze weather data, calculate optimal routes, and detect collision risks many times faster than humans. But the paradox is that most final decisions still have to wait for confirmation from the ground coordination system before being carried out.
If aircraft are already smart enough to understand the environment around them, why does the sky still need so many complicated coordination commands today?
The female engineer continues analyzing that the future of aviation may not lie in building many more radars or hiring many more air traffic controllers.
Perhaps the true future lies in turning each aircraft into an entity smart enough to coordinate with others in the sky in a more natural way. A young worker looks up at the aircraft being checked for its sensor system and realizes that aviation is standing at a moment when it must change its core operating philosophy.
The deeper cause of this change begins with the fact that modern air traffic has become too complex for humans to process perfectly with the old model.
The more aircraft appear, the more dangerous bottlenecks are created when the system depends entirely on centralized coordination. Whenever the central system becomes overloaded, the entire air traffic network immediately slows down like a city stuck in traffic because of a few important intersections. The future philosophy, therefore, begins to shift from centralized control to the self-awareness and self-coordination capability of each aircraft. Smarter aircraft will not only receive commands, but will also actively understand the position, speed, intention, and trajectory of the aircraft around them.
In the future, aircraft may be able to negotiate safe spacing and adjust flight paths within seconds without waiting for a chain of intermediate commands from the ground.
This does not mean humans disappear from aviation, but that the role of humans will shift from direct control to overall strategic supervision.
The young Hispanic workers inside the maintenance hangar continue checking new sensors designed to let that aircraft recognize the surrounding intents. Future aircraft will use artificial intelligence, real-time data networks, and predictive systems to understand risks before they appear.
When each aircraft becomes smarter, the entire sky can operate much more simply.
Simplicity here does not mean less technology, but less dependence on complicated chains of commands and less cognitive burden placed on humans.
A young worker realizes that this philosophy is like turning each vehicle in the sky into an element capable of understanding the whole system instead of only waiting for commands.
That helps significantly reduce the risk of errors caused by slow transmission, voice misunderstanding, or information overload in emergency situations.
The future of air traffic will not try to make humans work faster, but will make the system operate more intelligently by itself.
When each aircraft clearly understands the surrounding environment, the sky will no longer need so many overlapping coordination layers as it does today.
The biggest difference between current aviation and future aviation lies in the philosophy of handling the complexity of air traffic systems. The old model tries to control complexity by adding more people, more commands, and more layers of coordination. The new model instead tries to reduce complexity by allowing the aircraft themselves to understand and adapt to one another in real time. The male African engineer points to two simulation screens and shows that in the old system, overlapping flight paths create.
Meanwhile, in the future model, aircraft adjust slightly very early, so conflict risks almost never have time to form.
Aircraft intelligence is not meant to replace pilots, but to reduce the cognitive burden on the entire aviation system.
The sky becomes simpler because aircraft no longer depend on countless detailed commands as before, and can coordinate flexibly with one another within safe limits. Aircraft become smarter because they must understand not only themselves, but also the movement state of the entire space around them.
The male engineer realizes that the future philosophy of aviation is not really about going faster, but about reducing chaos more effectively.
The best technology is sometimes the kind that makes everything quieter and more natural, not more complicated.
The young workers complete the final inspection before the aircraft is taken out to the taxiway, under the gentle late afternoon lights behind the terminal.
Like sunbursts. All of them understand that the future of aviation will not be decided only by stronger engines or higher speed. A sky full of aircraft that still operates gently, steadily, and with fewer conflicts is the expression of a truly mature technology. Inside the clean and disciplined space behind the terminal, the young workers continue their familiar work as if they are quietly preparing for a sky